Okay, YouTube, in this video we're going to introduce the notions behind solving triangles, that is any type of triangle, not just right triangles, as well as the law of sines. We're going to do a very introductory example of it. So we say solving triangles, first of all, basically just means we want to find all the unknown measures in the triangle, so all three angles, all three sides. It's a pretty simple, straightforward thing to do. What we're going to do is we're going to focus on in these series of videos here, oblique triangles, so those that don't have a right angle in them, and so we kind of have to come away from our traditional conception of sine, cosine, tangent. But what I can tell you is you can solve any triangle given any three parts. And so what I mean is like two sides and an angle, or if you have two angles and a side, basically you can solve this triangle. So we have two laws that we tend to use more often than not, though. We say the law of sines, the law of cosines. And so again, we're going to focus on the law of sines in this video in a very introductory way. But essentially, when you want to use the law of sines, you must know two angles and a side. So we have an angle, angle, side, or two sides and an opposite angle. Okay, and so when we say opposite angle, we'll talk about what we mean there. It's kind of an important idea, but the angles and sides need to go in this order. Okay, and you can remember these, I guess, as S, A, A, S. But this one you never forget. If you spell it backwards, you catch my drift. So those go with the law of sines, and then these other two situations down here, three sides or two sides and an included angle, side, angle, side, we'll use a law of cosine. So as far as law of sines goes, essentially what it is, it's a proportionality between the angles in a triangle and the sides opposite in any given triangle. That is to say, like if we had some triangle here and we were to label this out, we say vertices A, B, C with capital letters, and then the sides opposite with lowercase letters. You would see that if you were to take the sine of this angle A and divide it by lowercase a, that would be the same value you get if you were to take the sine of B, which is a little bit bigger, and divide by the side opposite, which is a little bit bigger than A. And same thing with C. So as these angles grow, we would say that these sine values grow proportionally with them. So that being said, then we can express the law of sines as this. And so essentially, a lot of the time what we're doing is we're saying we know three of these values here, maybe capital A, capital B, lowercase b, and we want to go find the fourth, which is just algebra. So we're going to be solving proportions with these triangles. So law of sines. Okay. We say solve the triangle ABC if A is 32 degrees, B 50 degrees, and then we have lowercase c 18.7 degrees centimeters. So one thing I want to do is I want to take into consideration before I draw this what this might essentially look like. And so if I had a 32 degree angle, 32 degrees, maybe that would be like I could conceive of that being right here, this bottom angle, 32 degrees right there. And then B is 50 degrees. That's 90 would be, this way. So, like 45 degrees would be half of a 90. If this is a 90 here, it'd be about right there. So 50 degrees would be a little bit more. And then I'm thinking that our triangle would look something like this. So we have 50 degrees, 32 degrees, and then we could conceive of the bottom of the triangle as being right here. Okay, so essentially we're going to label this out with what we know. We know this is capital A. Capital B is this 50 degrees right here. And then this would by rights be capital C. And we know that opposite is capital C. We are given this side length is 18.7. And this is important that we label this. We label this in centimeters. Okay, get this out of the way here. So we're going to label this in centimeters just to be clear. Oops, wrong thing again. 1 second here. There we go. Centimeters. Okay, so when we solve triangles, it's just a suggestion, but I always tell people to make like a little data matrix off on the side and organize your information. I'll tell you one thing. If you can use the law of sines, and this is very true, we know that capital A is 32 degrees. We know that capital B is 50 degrees. This means we can solve for angle C by taking 180 minus those two. So we have 180. Minus those two would be minus 82. And we get 98 degrees. So I say this is 98 degrees. And we can go label angle C, 98 degrees, and we should. And then we know lowercase c is 18.7 centimeters. So the idea here is this. We can use the law of sines, and you can recognize this when you have what I call an angle side pair. That is, some angle and the length of its side opposite. Then we can use the law of sines, because what that does is it allows us to set up this base proportion value and then compare everything else to that value. Okay, so we are going to use the law of sines here to solve for these other two unknown sides. Let's take for example A or B. Which one do I want to solve for? I'll tell you what, B, it's just a habit, but I always say go big or go home. You want to solve for the longer of the two sides, or the bigger the two angles first. So if I'm going to solve for B here, what I want everybody to notice is that the law of sines gave all these as sine of the angle over the length of the side opposite. And you know what? If this is true throughout all of these values here, these ratios, then if you flip them over, they're also true. So since I'm solving for lowercase b, my suggestion is that we conceive of this formula as being interpreted this way this time. And so let's see, we're solving for b over sine b, and we know little c here, so little c over the sine of c. So we can plug in our values here and just solve for lowercase b. So we have b over the sine of b, which is 50 degrees, and then we say that this is equal to 18.7. There's a side length there, and that's in centimeters, and this is over 98 degrees, and we're taking the sine of that, so law of sines. Okay, so if we want to solve for b here, all we need to do is to get an exact value, just take both sides times a sine of 50. And this is a sine of 50 over 1, so you know what, we could combine this up a little bit here, but we say that b, first of all, is exactly 18.7 sine of 50 degrees. This is important that it's in degrees. My handwriting is horrible, sorry people. And then down here we have sine of 98. And so we need to evaluate this for its value. And so I have to be careful on my calculator. If you have a scientific calculator, you can type this in a little bit more easily, but we say 50 degrees. Let's start with this. The sine of 50 degrees, and I'm in degrees mode here. Take the sine of that times 18.7. So here's our numerator value. I'm going to divide this by in parentheses here. We'll go 98. We want the sine of that in parenthesis equals. So we get about 14.47. So this is about 14.47. And we need to label this. We also need to go label the triangle. So we say this is approximately 14.47. And that's in centimeters. Okay. And we should go write that over here also, 14.4. Now, how far you should go out on your decimal place here. I said 14.47. We could have gone further. The reason why I'm ending at the hundredths spot is because the original triangle had a value that went out most at the tenths. And we should agree we go one extra place value. So we say 14.47 centimeters. Okay, so the next question is that reasonable? It looks like it would be an entirely reasonable answer. And we could judge that now the length of side A has to be less than this because angle B was bigger than angle A. So now let's go ahead and go back and we'll just solve for A, and we'll do the same idea. We have A over sine A, since we're solving for lowercase a, and this is equal to the same base ratio that we used the first time, which was 18.7 over the sine of 98. We should use the given values as much as possible. 98. So now, again, and this A right here, my bad, this is 32 degrees, we know this. But essentially, we could take both sides of this times 32 degrees, and we get A equals 18.7 sine of 32 degrees on the right, and this is all over the sine of 98 degrees here, and we'll go ahead and get a value for this, but we get, okay, so clear, 32 sine times 18.7 equals, divided by, in parentheses, 98, the sine of that, in parentheses, equals 10.01. So this is approximately 10.01, and it was indeed in centimeters, and it was indeed less than what we had gotten for our b value, which it should have been this way. So I'm going to go label throughout, and that is how you use the law of sines. In the next video, we'll look at the ambiguous case situation 1. Cheers.